Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, back with a geometry video for you all, and today's lesson topic is all about transformations, and this is our part 2, which is our continuation from our transformations part 1 video, going in chronological order. The transformations part 1 video had a lot of basic definitions and vocabulary, as well as defining characteristics of transformations in geometry. So I would recommend that you watch that first, because there are a lot of concepts that I will be getting to, as well as the different types of transformations that I'll be referring to that you might be confused about if you don't already know them, or if you haven't watched my previous video. Everything is covered in that video, but I will try and make my best effort to reference those. But then again, that's not the main goal of today, because today's goal is to discover the higher level concepts of transformations and their actual applications in geometry. So I recommend that you watch that video before you watch this one. And before we jump into the meat of today's lesson specifically, please make sure to smash that subscribe button down below, hit that like button on this video, as well as hitting that post notification bell to get notified on any of our channel's latest posts at eCoreAcademy. So all of that's greatly appreciated. And let's get right into today's lesson. Today's lesson is Transformations Part 2 of continuation of Part 1. And it's all about what are the processes and relationships of transformation. So that's the theme of today's lesson. Now, this is a more high-level application of transformations. And like I said before, I highly recommend that you do some research on these concepts that I'm giving you, or better yet, just watch the part 1 video of transformations to get a full glimpse of what we're going to get into today, so that you're not confused. And today is going to be heavily revolved around the coordinate plane, as the coordinate plane has many accuracies in geometry, and transformations today are going to all revolve around the coordinate plane specifically, as we're going to enhance ourselves in algebraically. So I'm going to be reviewing the coordinate plane here for you guys in our first slide here. For the coordinate plane, I'm going to be reviewing the coordinate plane. I'm sure many of you are already familiar with the coordinate plane, as it was already involved in the algebra courses and pre-algebra courses as well. Coming into geometry, you're already expected to know these basic concepts and these basic figures as well, and these relationships. But I will just go over it, glimpse over it, because you're already expected to know this. So yeah, let's get right into it. How to represent transformations on a graph, and that graph is represented by the coordinate plane, which is basically the whole purpose of today's lesson. So the coordinate plane, by definition in geometry and algebra, is a plane in which the coordinates of a point are its distances from two intersecting perpendicular lines called axes. So this is an example of a coordinate plane here. And as you can see here, we have our y-axis here and our x-axis. So basically what a coordinate plane is when you have your y-axis, which is a horizontal line going up, vertical line going up and down, and you have your x-axis, which is a horizontal line going from right to left, and basically they both intersect at a common point, which is called your origin at 0, 0. So 0, 0. I'll write that down here. 0, 0. And at this point, called the origin, is when these two lines intersect at a perpendicular 90-degree angle. So they form a 90-degree angle, which makes all relationships between all of their coordinates and points alike. And a coordinate on a coordinate plane is basically a point on a certain plane given a numeric location, meaning if this, say for example, this is a point right here, that would be -3, 3, because of its defining characteristics with the x and y values given on the coordinate plane. So let's move into some more complex values with the coordinate plane, just to give you a little glimpse of the coordinate plane, as we'll be going through with this later on. So a function in a coordinate plane is a special kind of relationship or relation in which each value of the input value is paired with exactly one pair of the output value. So if you don't already know, for a function, the input is always your x value and your output is always your y value, and they both combine a singular coordinate in the form of x, y. So your x coordinate or your x number comes before the y value, and they're indicated within parentheses and separated by a comma as shown. So as we know that x is the input and y is the output, basically what's happening is if you're given the equation y equals mx plus b, or f of x equals mx plus b, what you're basically doing is you're taking one given value, you're plugging it into some kind of relationship or equation, and then after that value is plugged into that equation for substituting some type of algebraic value, you're then given an output, which is the answer of that simplified value, and what's put in is your input, and what's given out is your output, which is basically your solution of the problem, and I'll go into depth about that here. So graph relationships. So you have your input, which is part of a function, and the input is a number that will be used in a function rule to determine the value of the output. So it's what's plugged into an equation. So the equation for a function is f of x equals mx plus b. You are already expected to know that. That's your slope-intercept form, or your functional representation. F of x equals mx plus b. And what your input is it's this x value here. So x is basically what you're putting into the equation, and f of x is being the altering point of what's going to happen to this. And f represents the function, which is basically this equation out here, m and b, and you're going to somehow, in some manner, alter. So you're going to alter to develop a new answer, and that answer will then be your output, which is going to be some kind of change. Not necessarily always is going to be a change, but it's going to be some kind of altering to the original status of the input to develop an output, which is an amount that comes out of a function after the input has been derived and given into the function equation. So that is basically your y value that's given after your x value is plugged in. So x equals input, and your y value is your output. So now that we have these basics of coordinates and coordinate planes involved here, let's move on to what the whole theme of today's lesson is about: transformations. So transformations part 1. So we're going to look at transformations and the representations on the graph. So if you don't already know and you haven't referred to my first video, and also just as a recap for those of you who have watched my video, transformation basically is a one-to-one mapping between two sets of points. So if you have ever seen an example or know what transformations are, which you're expected to know what they are by now, a transformation is some kind of altercation to some kind of altering to a point in location-wise that in turn changes an entire figure. So what a transformation does, it basically moves figure's points a certain amount of distance in order to shift the entire figure. So you're shifting the figure in some kind of manner under the three main types that we're going to go over today, the three main rigid motions. And I'm going to show you a little example here. Say, for example, we're given a plane here, right here, a coordinate plane. And we're given one value. This is going to be like a little scope of magnification of what I'm showing you here of the first plane. So let's say, for example, this is our original triangle given here. And basically, we're trying to shift it down. Say, for example, we're just trying to shift it down a certain amount of units. Well, what you would do is you basically move each and every separate vertex of that triangle to get a completely new triangle, which is basically moved downwards from the original triangle. So that's a transformation. It's basically just a change in position. Change in position. All right. And just as a little heads up here, the first type of transformation format that we're going to look at is a blank transformation. And as I showed you in the previous video, transformations part 1, it's all about our blank transformations. All the visuals that I show you are all blank transformations. And a blank transformation is simply when a transformation has only visual representation on a blank plane calculated through estimation. So say, for example, you're trying to show this same value here. You're trying to show a simple triangle here, and you're saying that you want to move it across this distance here. And that's a translation vector showing that you're going to shift this figure on a horizontal lateral. And once you're shown that, you're just going to basically move it off of what you see visually. And it's a rough eyeballing estimation, and that's your blank representation, blank transformation. And that representation does not show any calculation involved in this. So there's no units involved, so we don't know what units are in this. So it's a very amateur way of showing it. It's just simply showing what that transformation looks like in general. So we're not giving any information to trace back to what we're originally given before this actual transformation occurs. So the issue with that is we're not able to put any numbers or algebraic terms to that, and therefore it's not necessarily a relevant information to us. But we're going to look at what's actually important today, and that's coordinate transformations, which basically heightens what's given in blank transformations. So a coordinate transformation is when a transformation is represented algebraically and can accurately be represented on a coordinate plane. So like I said before, blank representation of a transformation does not have any sort of numeric value or algebraic value, so we're not able to put a certain estimation to it, an accurate estimation to it, and we do not have exact trace value for a description or a writing of it, a visual of it. So basically what a coordinate transformation does is it takes a figure and it puts it on an axis in which it can be defined by specific points, which are given by coordinates and specific numbers. And as you're able to do that, you're able to calculate the amount of distance that you're moving that figure, and you can represent that in terms of numbers and algebraically in equations. So an example of that would be if we draw another coordinate plane here. I'm just going to reinstate what I said before with the triangle. This is a little magnification here. The triangle here, we're trying to move it. Let's say we're trying to move it right. Let's just say we're trying to move it right here. But when we're given that value, the axis to move it right, we can define it by units or points, since the coordinate plane actually is defined by exact given values and points. So when we're moving that, we're going to move it over 5 units exactly. So each point is shifted over 5 units under this translation. If you don't already know what that is, it's a shifting of a point and entirely a figure. And we're given exact values here so that we can represent this through specific coordinate rules, which I will get into for each and every specific type of rigid motion transformation. And there are specific coordinate rules that define each type of transformation, like I just said, and we will get into that. So these are specific coordinate rules, basically little cheats that you can use to simplify your transformation on a coordinate plane. All right, so for our first type of rigid motion transformation that we're going to get into today is our rotations, part 1. And this is all about the rotation process. This is an overview, not necessarily what's given in the combustible parts with given specific given values. So in order to conduct a rotation, you will need the angle of rotation, which is given in degrees, and the center of rotation, which is a specific point. Now, remember how I said the angle of rotation, this is supposed to say rotation. Remember how I said the angle of rotation has to be revolved around some sort of unit, and that's our degrees, and it also has to be revolved around some sort of point, and that is our center of rotation. So the center of rotation is basically when a figure is rotated by a certain angle of rotation, what's going to happen is all other points are going to be obscured for that single figure in relation to its environment originally, except the center of rotation. It's always going to stay the same because that figure is going to be rotating around the center of rotation, and this is basically the central point where everything's rotated about. But the center of rotation now is always going to be the origin at 0, 0. So when I'm talking about the center of rotation, that'll always be the origin. So the center of rotation will always be representative of everything being put about the origin. Fix this here real quick. There we go. So that's always going to be 0, 0, and it's going to be put in the form of about the origin. That's always going to be the center of rotation. And your angle of rotation is always going to be interchangeable, meaning the angle of rotation will always be representative to a specific value. So that's from 0 degrees to 360 degrees in our case, but you can always rotate it to a maximum amount of degrees. It'll just overlap these values given. All right, rotations part 2. This is going to be coordinate rules for rotation. This is really what we're here for, the defining characteristics and rules of rotations on a coordinate plane. So these are its applications. So if you're rotating a figure 180 degrees about the origin, you're basically going to change your points from x, y, to negative x, negative y. And then for rotation 90 degrees clockwise about the origin, which is basically, think about it clockwise this way. It'll be the way of a clock goes. For me, it'll be the opposite of what you're saying. So for you guys, it'll be this way. So that'll be clockwise for you, which is basically just a positive 90 degrees about the origin. So you're taking x, y, and you're changing that and altering it to y, x, negative x. And finally, for rotation 90 degrees counterclockwise about the origin, which is basically negative 90 degrees, that's going to be negative y comma x, which is simply altering x comma y to negative y comma x, and that's the opposite of y right there given to you. And this is a plane, so say, for example, we're given a point here at negative 4 comma 4, right here. And we're trying to rotate this point 180 degrees about the origin. We're going to show that by looking at this coordinate rule, negative x comma negative y. So you're taking the opposites of both values of the coordinate. So the coordinate that you're given here for this point that I've indicated about this giant yellow blob is negative 4 comma 4, and that's going to be indicated by 4 comma negative 4. You're just inversing each value. So that's negative 4 comma 4, negative 4, and basically that is a 180 degree rotation. So what you can think of is each and every coordinate is going to be a 90 degree rotation. Quadrant. So each quadrant, which is each grid sectioned off by x, y value intersecting by a 90 degree angle, is going to be worth 90 degree rotation for any figure. So this will be 90 degrees here, 90 degrees here, and this will be 360 degrees by the time you're back. And when you add two 90s together, you're getting 180 degrees. And no matter what direction you go, from this way, this left side, or the right side over top, it's always going to equal 180 degrees. But for 90 degrees, counterclockwise and clockwise, you're going to the nearest quadrant, that negative 90 or that 90 degrees indicated. So now let's apply these coordinate rules into an actual problem here. So the problem that we're given is rotating this triangle 180 degrees about the origin, and we're going to graph that as well. So it's important to graph so that you actually look at the visual representation of what that rotation is going to look like on a coordinate plane. So we're going to rotate this triangle 180 degrees about the origin and graph it. So basically we're going to look at our coordinate rules. So if we take x comma y here, we know that our coordinate rule for 180 degrees is going to be negative x, negative y. We're just basically putting in the inverse or the opposite value of each and every given xy coordinate. So we're going to look at our first coordinate. We always flip every point and then connect the segments to get the whole triangle. So we're going to look at point number 1, which is 1 comma 3, point A, and we're going to put that under a rotation, which is going to be basically flipping, adding a negative sign to each value to get negative 1 comma negative 3, basic multiplication right there. And then for point negative 2 comma 1, we're going to add a negative value to each one of those coordinates, and we're going to get 2 comma negative 1. And finally, for our third coordinate, we're going to get 4 comma 2, and then add the inverse of each and every coordinate point to get negative 4 comma negative 2. And now we're just going to graph that on our coordinate plane here. So we're going to start with negative 1, negative 3. We're going to graph that down right here, and then 2 comma negative 1, and negative 4 comma negative 2. Here we go. That's clearly a 180 degree rotation. I'm just going to erase that real quick. My line was really bad there. Sorry. If we draw that from here to here. All right. That's our new triangle transformation under a rotation about 180 degrees about the origin, and we just graphed it. Now we're moving on to reflections, number 2 of 3 for our rigid motion transformations. This is our part 1. So what are reflections, and what properties of reflections do we need to actually carry out this process? So in order to conduct a reflection, you must know the line of symmetry in which your figure will reflect across, and the coordinate rules are only specified for the most common of lines on the graph. It will work otherwise, even if you don't have that, unlike rotation. So in order to conduct a reflection, you must have your line of symmetry where the actual line is being reflected across, just like a mirror. And you need to be indicated that with some sort of equation in the form of y equals mx plus b, or any type of formatted line equation, but we're going to be using y equals mx plus b for all of our examples today. So that's an indication of our lines of symmetry, specifically on a coordinate plane. And the coordinate rules that we're going to give you here for reflections are most common, are only for most common of lines on the graph, but it will work otherwise. So basically what I'm saying is coordinate rules are shortcuts. They're merely just shortcuts on a coordinate plane trying to conduct a transformation. And all that's showing here is, so shortcuts. And all that's showing here is that you don't necessarily need to use these shortcuts to actually conduct a reflection. For a rotation, you must use those rotation rules to do any type of rotation. You can only rotate it in increments of 90. But for reflections, you don't necessarily need to. So if you're given a line of reflection, and say for example you have line point A, okay, you have point A here, and then you have point B here. You don't necessarily need to use our coordinate shortcuts that I will show you later, but all you need to do is calculate the distance of one point from the line here. Say, for example, it's 5 units. Then you can automatically discover how the point of point B and its distance, which is 5 units. Because in all, reflection of 2 points is basically that they are the same distance from the line of symmetry in opposing directions, meaning completely opposite directions. So let's get into the coordinate rules of reflections. So reflection across the y-axis, which is one of our simple lines, it's basically the up and down horizontal vertical line of a coordinate plane. So the reflection across the y-axis is xy mapping to negative xy. So you're just putting the inverse of the x value. And the rule for reflecting across any axis given on the coordinate plane, meaning the y or the x-axis, you always inverse the opposite given coordinate. So if you're reflecting across the y-axis, the x-coordinate will always be the opposite. But if you're reflecting across the x-axis, your y-axis will always be the inverse. So it's always the opposite. So y-axis, it'll be negative xy, you're inversing the x value. For the x-axis, you're inversing the y value, so it'll be x comma negative y. And then finally, for our next line, it's going to be reflection across the line y equals x, which is the common horizontal point in the coordinate plane, and it'll map from xy to y-axis, so you're just flip-flopping the coordinates. And what that looks like here, this is your y-axis here. It goes up and down right here. Right here, I'm highlighting that here. And then you have your x-axis here, and it's moving from left to right here. And then finally, your line y equals x will basically just intersect the origin, and it's a horizontal line splitting this coordinate plane in half on a diagonal. And that'll be y equals x right here. So y equals x. Whoops. So that'll be y equals x right there. So let's look at a problem for reflections. We'll actually plug this into a problem. So we're going to reflect this figure across the y-axis, and this y-axis is shown here. And since we already know our rules, we can just go ahead, and since it's y-axis, we already know our rules for y-axis reflections, we can just simply go ahead and plug in these values to what we already know with their coordinate rules. So a reflection across the y-axis maps the coordinates from xy to negative x, y. We're just reversing the opposite coordinate given. So if we're looking at our first coordinate, negative 3 comma 1, we're merely just going to plug in this value here, and we're going to describe the opposite value of the x value and keep y the same. So that'll be 3 comma 1. I'll just write that here. Make that a bit easier. Equals 3 comma 1. Not equals, but moves to. And then for a second one, we have 1 comma 3. And I'm just moving clockwise here with my points, my selectiveness of my points. So it moves from negative 3 comma 1 to 1 comma 3, which is indicated by point B. And that basically maps to our coordinates of negative 1 comma 3. Because all we're doing is changing the x value, but keeping the y value the same. And then for our final third coordinate, we have 2 comma negative 4. Now mapping to under a reflection across the y-axis to negative 2 comma negative 4. And we're just going to graph this as well. It always doesn't hurt to graph because it always shows you an accurate visual representation and relation, just to give you a good example and to check yourself and what you're doing. So we're going to graph these coordinates right here. these are new transformed figure of triangle ABC to A prime, B prime, C prime. So we have point 3 comma 1 here, point negative 1 comma 3 right here, and point negative 2 comma negative 4 right down here. So we can just draw those lines, connect these points that we've already graphed, and we are good and done. So like I said in the previous video, I just want to add this here. If you're given any describing symbols or especially letters for any points of your original pre-image before a reflection occurs, say for example, we're given here triangle ABC. What you're going to do for a transformation is you're going to basically put the prime of that value. So that's just basically like a little comma at the top, and that's representing our new value here, our new triangle here. All right, final one, translations. Thank you guys for pushing through with me in this grueling lesson, but it's important that we get through all of these. I know it's a lot of notes to take, but keep in mind that this is an enrichment course, so I'm trying to throw these fundamentals at you so we can heighten our concept and our course material for you all, so that you are understanding of what we're doing, and we can slowly elevate ourselves all the way up to where we exactly want to be. So the translation process. So the translations are conducted through translation vectors on blank planes. So just how rotations and reflections have lines of symmetry, angle of rotations, and centers of rotations. Translations have translation vectors, which are represented on blank planes. However, they can also be shown and given an accurate representation of final transformation on the coordinate plane as well. And translation vectors on a plane can only move up and down, as well as left and right in direct and non-horizontal lines. So basically what I'm saying here is transformation, if you don't already know, which you should know, is when you slide a figure across, is basically when you take a point and you slide a figure. You're basically just shifting it. So if you're having a triangle, you're going to shift it in any direction, any non-horizontal, or any direction. It could be horizontal, up, down, left, and right, or anywhere that you want to go. And that's only on a blank plane. So remember, blank plane is not on the coordinate with specified points. But translation vectors on a plane can only move up and down on a coordinate plane. I'm saying here, so coordinate. They can only move up and down, as well as left and right, and indirect and non-horizontal lines. So what I'm saying is, on a blank plane, you can just move any direction that you want. You can move in a horizontal line if you want to, for these 2 points, point A to point B. However, on a coordinate plane, to move from point A to point B, similarly, to get the same answer, you would basically, all you have to do is move left a certain amount, right a certain amount of units, because remember, coordinate plane always includes values and specified numbers to represent distances, and then you'd move up a certain amount of points. So right a certain amount of points and up a certain amount of points, but you'd still get the same answer as a horizontal line. So it's still the same answer. It might seem a little tedious, but with our transformation rules, it's way quicker than anything, I'd say. And with our coordinate rules on a coordinate plane, it's just way easier than even writing it out on a blank plane. You can simply just plot that point. So let's look at our coordinate rules for translations. So in a translation, you can add the value of units that you need to move up and down in a translation to the y coordinate and the value for the horizontal shift to the x coordinate. So just breaking apart what that means, I know that's a long definition, but it's very simple in terms of its concept. So you can add the value of units that you need to move up and down, simple directions in a translation. You can add that to your y coordinate. Since the y coordinate represents a vertical axis, it's all up and down motions. And then for the value of the horizontal shift to the left and the right, basically horizontally, can be added to the x coordinate, since the x axis represents horizontal movement, moving from the left and the right. So simple translation rules is when you're moving, translation rule when you're moving up and down in any manner, it's x and y maps to x comma y plus t, and t is just basically the distance that you're moving. And that's up or down, like I showed you here. And t is always going to be consistent in every one of these rules. So translation rule up and down, you're going to take x comma y, and then if you have certain units that you need to shift, so say for example up 5 units would be +5, and down 5 units would be -5, because if you're moving up, you're going positive, down is negative, so I'm going to write that here. So negative equals down on the y-axis, and for the x-axis it would be to the left, moving to the left, and then for positive on the y-axis that would be up, and on the x-axis that would be to the right. So if you're moving up and down, that would be x comma y plus t. For the translation rule right to left, which affects the x-axis, would be x comma y mapping to x plus t comma y, which are affecting changing in the x coordinate. And if you're trying to do an overall shift, meaning moving up or down and left and right at the same time, that would simply be x plus t comma y plus t, because you can always conduct a translation at the very same time. And finally, guys, this is our last slide. It's going to be our problem page. This is going to be a problem that we're going to represent our translation with. So we're going to translate the figure 3 units down and 4 units to the right. So I'll just write that here. So we're going to translate it 3 units down, because remember how I said down is negative, so it's going to be -3, and then 4 units to the right, so 4 units right is a positive movement, so it's going to be +4. So we're going to translate this figure, so we're going to translate each and every single one of its separate points. It's going to be transformation of each separate points under a translation to develop an overall transformed figure of this original triangle ABC. So first step, we're going to take our first point moving clockwise, so we're going to take point B, which is -2 comma 1. We're going to transform it under this translation. So basically what that is we're going to take this and we're going to use our translation rule to get that. We're going to subtract 3. Sorry about that. That's wrong here. So we're going to add 4, because remember, moving right and left affects our x coordinates. So we're going to add 4 here because we're moving right 4. And then we're going to subtract 3 because we're moving down 3 on the y coordinate. And that basically equals -2 plus 4 is 2, and 1 minus 3 is -2. So that's 2 comma -2. For our second point, 1 comma 3, which is on point represented by point A, we're going to be taking the coordinates 1 and 3. We're going to be altering it under our translation rule. So we're going to be adding 4 because of the effect that moving right affects the x-axis. And then we're going to take 3. We're going to subtract 3 from it since it affects the y coordinate. And we get our final coordinate value as 5 comma 0. And finally, we have our third coordinate, which will be our 4 comma 2 coordinate. We're going to apply it under this translation rule, and we get that 4 plus 4, we're going to add 4 to 4, and then, and then we're going to add 4 to 4, and then subtract 3 from 2. And finally, that equals 8 comma -1. Now, I know you guys might be thinking, how are we going to graph this? I didn't specify to graph this necessarily, but what I do recommend is that you guys go back, try this problem again, and it's an incentive for you all to try graphing it yourself. And it's a little challenge that I want you to do. I want you to take a blank piece of paper, and I want you to develop your own coordinate plane so that you feel very comfortable, not only visualizing it, but drawing it, showing your skills and representations with your better understanding of it. And what you're going to do is you're going to go back and you're going to calculate these points, sorry about that, and basically graph them on your own made coordinate grids and see if it looks like an accurate transformation of this original given triangle ABC. Alright guys, I hope you guys enjoyed this video. This has been eCoreAcademy e-learning platform today. I know this is a very grueling lesson, but it's very important as transformations are very important in geometry as a whole concept itself. Now, we put a lot of effort into these videos, so please make sure you guys like and subscribe to show your support, and hit that bell to get notified on any of our channel's latest posts at eCoreAcademy. You can please feel free to visit our website at eCoreAcademy.org, and this website is definitely a bonus, as we have just put in a lot of time and effort to fully enhancing it and developing it to where it's a curated experience in which you get full unlocked access to all of our YouTube videos made here. And you can also get organized course studies in which you're given integrated quizzes, note sheets, and worksheets on each and every course and subject and lesson video. So I highly encourage you guys to make an account on our website for absolutely no cost, so that you guys can develop yourselves and enhance yourselves as enrichment learners. And also, if you guys want to email us for some reason, to contact us for any questions, if you just want to reach out to us, please email us at eCoreAcademy@gmail.com if you just want to open a line of communication. And finally, please contact us please visit all of our socials in this description box below, down below the video, with all of the links, which is our Facebook page, our Instagram page, and as well as our Twitter page. And here we have all of our, our social media posts. And please feel free to share those videos, communicate with others, and provide some of these videos to those who might need help and find them useful. So once again, guys, hope you guys enjoyed this video. I had a pleasure making it, and I hope you guys are all doing well and staying healthy during this COVID-19 pandemic. And on that note, I will see you guys in the next one. This has been AJ, and I'll see you all later. Peace.